Listen, if you've ever wondered what really separates a standard developer from a staff-level systems architect, well, you're in the exact right place. Welcome to this explainer. Today, we're totally demystifying the network edge. We're going to break down the hard-earned architectural patterns that senior engineers use to prevent those catastrophic late-night production failures. So, let's just dive right in.
Picture this scenario, because we have all been there. Your CI/CD pipeline is glowing bright green. Your test coverage is sitting at a solid 90%, and your Kubernetes pods, they're purring along with literally zero restarts. But your entire application is completely paralyzed. Users are getting hit with endless 403 forbidden or 502 bad gateway errors, right? So how exactly does perfectly healthy code just fail in a production environment? Well, it happens because of the massive gap between your application logic and the actual physical reality of the network.
And this right here brilliantly illustrates the mindset shift you absolutely need at the senior level. Juniors, they joke about the scream test, turning off a server and just waiting to see who screams. But in a serious enterprise environment, that is a straight-up career-ending move. Professionals use network telemetry. Instead of guessing or crossing their fingers, senior engineers are analyzing cloud provider flow logs. They build a perfect mathematical dependency graph before they ever touch a single node. They don't guess, they observe.
All right, bringing us to Act 1, balancing requests, not connections.
Let's start with the illusion of load balancing. Almost every single team falls into this trap when they first adopt gRPC for internal communication. Here's the deal. Because gRPC uses HTTP/2, it multiplexes multiple requests over a single long-lived TCP connection. So if you're using a standard Layer 4 connection load balancer, it's going to funnel that single connection to just one pod. The result? That one pod gets absolutely hammered, creating a massive, crippling hotspot while all your other pods are just sitting there completely idle. To fix this, you absolutely must move up to stack to Layer 7 to balance the actual requests, not just the connections.
Now you might be thinking, okay, I'll just drop in a service mesh like Istio. That's the easy fix for Layer 7 balancing, right? But a senior engineer knows the hidden trade-offs here. Introducing a service mesh adds a latency overhead of about 1 to 3 milliseconds per network hop. And in a modern distributed system where a single user click might trigger, say, 30 internal microservice calls, that latency compounds incredibly fast. You don't just blindly deploy a service mesh unless your traffic volume and complexity mathematically justify that performance hit. So, what's the move? How do we build guardrails without totally over-engineering the whole shebang? Well, instead of blindly deploying that service mesh, a senior engineer will update the application code to set a max connection age, let's say 5 minutes. What this does is force your gRPC clients to periodically drop and reconnect, which naturally rebalances traffic across the cluster. On top of that, they ensure all external traffic enters through a properly configured Layer 7 ingress proxy, and they set up automated alerts on the coefficient of variation across the pod fleet. You don't just trust the load balancer to do its job. You verify the distribution mathematically.
Moving right along to Act 2, the payload trap.
Let's examine the absolute nightmare of edge drops. It is wild how a completely standard development practice can create a catastrophic infrastructure failure before your code even has a chance to execute. Here's what happens. Developers love stuffing everything into a JWT, roles, permissions, and maybe 25 different Active Directory group names. But here is the hard reality of network physics. An AWS application load balancer has a hard, non-configurable HTTP header limit of exactly 64 kilobytes. If your token bloats past that limit, the load balancer instantly drops the request. Your users get a connection reset error, and your Kubernetes logs show absolutely nothing. Why? Because the request never even reached your cluster. It's a ghost.
Now, the senior fix here isn't to go in and start tweaking proxy buffers. It's payload standardization. You absolutely must mandate that the JWT only holds the bare minimum, basically just the user ID. The edge proxy then forwards this incredibly light request into the cluster, and your downstream microservices query a high-speed internal cache, like Redis, to resolve all those group memberships and permissions. You have to keep the network edge incredibly fast and incredibly lightweight.
And when things do inevitably go wrong at the edge, you need to be able to isolate the blame immediately. This brings us to the golden metric of proxy debugging. Always compare your upstream response time against your request processing time. If the upstream time is, say, 50 milliseconds, but the total processing time is 5 seconds, boom! You've instantly proven that the application code is blazingly fast, but the network proxy is struggling to buffer data, or maybe the client is just on a terrible connection. Looking at it this way stops the developer versus ops finger-pointing instantly.
That brings us to Act 3, surviving the butterfly effect.
We really need to talk about system resilience and the devastating chain reactions that happen when a minor downstream service hiccups and ends up crushing your entire API gateway. Look, in distributed systems, failure is inevitable, but a lack of circuit breakers transforms a minor, everyday degradation into a full-blown retry storm. This is the butterfly effect in action. A localized failure triggers automated clients to retry. Then, the clients of those clients retry. Suddenly, your services are completely overloaded, trying to serve your regular baseline traffic, which is now compounded by an exponential, self-inflicted flood of automated retries. Your own infrastructure is effectively launching a denial-of-service attack against itself. No bueno. Junior developers usually try to solve this with simple timeouts. But simple timeouts just cause these cascading waterfalls of waiting, where each network op waits its full timeout duration while the poor end user just stares at a spinning loading wheel. Senior engineers, on the other hand, implement propagating deadlines. The initial gateway sets an end-to-end budget, let's say 500 milliseconds. As the request travels through the microservices, each downstream call only consumes whatever time physically remains in that budget. If the clock runs out, the system aborts early. You save compute resources, and you fail fast.
If you want to truly control your P99 tail latency, and remember, that's the latency experienced by your slowest 1% of requests, you absolutely need these 3 controls. First up, jittered retries. This adds randomness to your backoffs, so thousands of clients don't all retry at the exact same millisecond. Second, circuit breakers. These route traffic to a fallback mechanism the second a service degrades. And third, the bulkhead pattern. This isolates tenant resources, meaning a massive traffic spike from one single power user doesn't consume the entire connection pool and ruin the experience for everyone else.
All right, let's jump into Act 4, impotency at the edge.
When you're trying to survive failovers and retry storms, how do you make sure you don't accidentally charge a customer's credit card twice? Well, let's look at Stripe. They process over $640 billion annually, so they illustrate this concept at an absolute extreme scale. They manage item potency by using Redis for lightning-fast deduplication key lookups. They apply a strict 24-hour time to live on those keys to keep storage growth under control, and, this is crucial, they cryptographically hash the request parameters. That ensures a buggy client can't just reuse an old key for a completely different transaction.
The core mechanism driving all of this is the idempotency key. When you're dealing with unreliable networks and distributed latency, the client, and I want to emphasize that, the client, not the server, must generate a unique UUID for the transaction. When the server receives the request, it checks a deduplication table. If that key already exists, the server knows, okay, this is just a retry of a successful task, and it safely returns the cached response without re-executing those expensive database writes.
But honestly, here is where system design gets really difficult. Think about designing a system where idempotency keys are passed hierarchically across 20 different microservices. This forces staff engineers to deeply consider cap theorem trade-offs. During a network partition, do you reject the request to maintain perfect consistency, or do you accept the request to maintain availability, but risk creating a duplicate record? There are no easy, one-size-fits-all answers here. There are only calculated trade-offs based on what your specific business requires.
Which brings us to our conclusion, the Senior Edge Playbook.
Let's bring all these hard-earned architectural paradigms together into a practical playbook, stuff you can actually start implementing in your own environments next week to bridge that gap between perfectly written code and perfectly running systems. Number 1, treat your network proxy as a first-class application in its own right. It needs the exact same strict tracing, linting, and observability as your core business code. Number 2, make P99 latency your headline metric. Number 3, never ever perform a network call inside a database transaction block. 4, standardize your edge payloads to keep them incredibly light. And finally, number 5, isolate your tenants with bulkheads before you even attempt to scale.
Listen, technical debt at the network edge is a silent business killer, period. When a competitor launches a flashy new feature and your deployment is just paralyzed by 403 errors and environment drift, the business loses real money. True visibility has to precede any attempt at modernizing or scaling your distributed system. Because the hard truth is, you simply cannot safely accelerate a system that you do not mathematically understand.
So, I want to leave you with this final provocative thought. Are you actively architecting your API gateway to survive the harsh, physical realities of distributed network failures? Or are you just treating the network like it's magic and hoping your code is perfect? Because I promise you, when the butterfly effect hits your infrastructure, hoping for the best is literally a career-ending strategy.
Go review your edge architecture today, pull up your network telemetry tomorrow morning, and start building systems that actually survive production. Thanks for joining me on this explainer. I'll catch you in the next one.